Okay, we looked at a problem of a circular cylinder which is moving with some time-dependent speed. And this time we assume the cylinder is moving in the x direction. And then the boundary value problem for this guy is the same as before. Um, so velocity at infinity, um, velocities at infinity have to vanish. And the boundary condition this time is d phi dn, which is gradient of phi dot n, right? Has to be the same as the body normal velocity of the body, so which is u dot n. And this time u has only x component. We can write this as u and x. And this particular problem, we use moving coordinate. So coordinate system which is fixed in the cylinder. So in that case, the radius, this radius is still a, and I think I use r, or I forgot, but I think I use a. So this coordinate system is fixed in the cylinder. So the radius of the cylinder is always the same as a. So at r equal to a. And then nx is normal direction is toward the cylinder. So this is normal, and the x component is nothing but minus u cosine theta. So in this setting, this is exactly the same as having circular cylinder with incoming flow, and therefore phi can be written in terms of dipole solution, and that is nothing but u minus ua square cosine theta. Okay. So I hope that everything up to this point is clear. If not, it's not good for when you take an exam. So you should know this at least. Okay, now I mean, if the cylinder is stationary, when we have a uniform flow, then we had the velocity potential for the uniform flow here. But this time, since body is moving, but fluid at infinity is 0, so that's why we don't need uh, the velocity potential for uniform stream. And but this time, this phi, it depends on time, which is here. Okay, so u is a function of time, and therefore when you compute in hydrodynamic pressure, which is P is minus, this is hydrodynamic pressure, is given by rho dV dt, and therefore we have minus rho u dot r a square cosine theta, and the hydrodynamic force is given by, which is a vector, given by P times normal vector times the body surface. Okay. So this is a very general the representation for inviscid flow. So this is hydrodynamic pressure, and this is hydrodynamic force, and we just substitute that into here, and then we have rho u dot. This dot means time derivative. So this is d dt, and then we have. I have to evaluate this guy at the body surface, right? We are evaluating pressure. We are integrating pressure over the body surface, so we have to evaluate pressure on the body surface, and therefore we have A in the denominator, and then A squared cosine theta, and normal vector can be minus cosine theta and minus sine theta, right? So this guy has x component and y component, which is x. This is theta, and therefore this is theta. So I have cosine sine. And ds, this is the area, or in two-dimensional problem, we are looking at hydrodynamic force per unit length, right? Because we are not integrating in the perpendicular direction. So we have a d theta. So that will give us hydrodynamic force per unit length. Okay. And integration has to go from 0 to 2 pi because we move around the circular cylinder. And I have when I have cosine theta times sine theta, if I integrate over the 0 to 2 pi, that is 0. Okay, and so what Fy is identically 0. X component of hydrodynamic force is rho u dot from 0 to 2 pi, and then I cancel this guy out, so I pull out the radius a squared, and then I have a cosine square theta d theta. Last time I said this is a pi over pi, because this is a 2 cosine, 1 minus 2 sine 2 theta, right? No. So this is 2 cosine square theta minus 1 is cosine 2 theta. So cosine theta squared is 1 plus cosine 2 theta divided by 2. And integration of this part goes 0 because it's periodic. And not because of that, but the property of cosine. And then 1/2 gives 1/2 times 2 pi, which is pi. Okay. So at the end, what end up with f of x is rho of pi a squared times u dot. Okay. I don't think the sign is right. The body is moving in this way, force is that way. So I messed up, sign somewhere. Let's see. So I have minus here. Oh, I have originally phi has a negative sign there, so I should have a plus here. Okay? Because I have minus sign here, and I have minus d phi dt. So I have a plus sign here, and that changing on this, and then I need a minus sign, and I have a minus sign here. Okay? Then it physically makes sense when you're trying to move this guy to this way, and this cylinder experiences, a force, hydrodynamic force. we learned that if this guy is moving with a constant speed, then this body doesn't experience any force in an inviscid case, right? So for viscous case, you of course, when cylinder is moving, hydrodynamic force is applied to the cylinder because the friction around the cylinder, and also there is another thing which we call foam drag due to the separation. Okay, so because of those two, the circular cylinder experiences force. But for an invasive case, the force was identically zero. But this time, when the cylinder is accelerating or decelerating, then you definitely see a hydrodynamic force, which is not non-trivial. So this is acceleration of the body, right? U is the velocity of the body, so acceleration of the body. So whenever a body is accelerating or decelerating, there is a force. You have to apply force to accelerate the body or decelerate the body. Okay. And if you look at this guy, this pi a square is nothing but the area of circular cylinder and times the density of fluid. So in terms of the dimension, this is area times density, which is the mass divided by length. But we divide by length because we are looking at 2D problem, right? In 3D problem, you will have just this is a dimension, okay? And so basically we have mass times an acceleration, okay? So this particular part is called the eddy mass. You shouldn't be confused with the real mass of the body. This is a mass area or volume multiplied by density of fluid, not the density of the body. Okay, so you shouldn't be. You have to distinguish, those two. But anyway, so whenever you accelerate the body, you have to accelerate the fluid as well. Okay, because of that, you have to apply, this additional force, and that's why we call, this is eddy mass, and also this guy has a dimension of mass. Okay. So whenever the body has the acceleration or deceleration, in any case, you expect this kind of for additional force, and so when ship is floating on the surface, on the free surface, ship is moving with an acceleration, and then you expect this kind of extra force because body has an acceleration. So is it clear what the eddy mass is? So when body is moving, you accelerate the fluid around the body, and that's why you need extra force. Okay, as a simple example, Suppose you have a circular cylinder free falling. So gravity is acting this way, right? So I want to know the speed of this guy. Okay, when I let it flow, let it drop, and so let's say this guy is moving u, which I don't know yet, okay? And so I'm trying to find the u at this point by writing equation of motion, okay? So we use Newton's second law, right? So what do we do? So we say this circular cylinder has a mass m of b, m sub b, okay, times u dot, okay. So that's the mass times real mass of the cylinder times the acceleration. That has to be equal to the force applied to this cylinder, right? So what do we have? First of all, since this guy is function of time, or this guy is accelerating or decelerating, therefore we expect added mass term or additional hydrodynamic force, which is acting in the opposite direction. If this guy is falling in this way, the hydrodynamic force is acting this way. And now we know what the added mass is. So in terms of direction, it's a negative. And then we write added mass m. So let's call this guy m, small m, okay, times u dot. Okay, that's exactly what we have. If it is circular cylinder, m is nothing but rho pi a squared. So this added mass is rho pi a squared. And the other part is what? This guy is falling due to gravity. So gravity is pulling. So this guy has to experience body force, which is, I have positive sign because this is positive direction to me, because the direction of gravity is the same as the direction of the motion of the body. Then what else do we need? Is that it? This guy has feels hydrostatic force. Here we computed only hydrodynamic force. So hydrostatic force has to be included, which is the buoyancy. And the buoyancy has to be the opposite direction. So rho. So this is volume, this is mass, and this is volume of the body times, right? Do you agree? That's the buoyancy, right? And so this guy, I can rewrite this as rho. Actually, you know what? Let me write this as a rho. This time, it's not the area, it's volume, it's area times g, right? So that's the area of this circle. And this is rho b times pi a squared. This rho b is density of the body, not the density of fluid. And then I can rewrite this as rho b pi a squared. So now you see pi a squared everywhere. So you can drop pi a squared, and then I end up with rho b. When I move this guy to the left-hand side, I have rho b minus rho g. Okay. So u dot, which is acceleration, is equal to that's what we end up with. Okay. So if rho b is much greater than rho, which rho b is again is the density of the body. If rho b is greater than rho, in other words, the body is much heavier than fluid, and then this guy. So first case, rho b is much greater than rho, and then u dot has to be g. On the other hand, if rho b is much less than rho, then we have minus g. Okay. So the body is much heavier than fluid, then the acceleration is nothing but a gravity. On the other hand, if fluid is much heavier than the body, or the body is much lighter than fluid, then the body is moving, has an acceleration of gravity in the opposite direction. But the general case, that's the expression for the acceleration. So here, this is a term that we have to include from hydrodynamic, force. Okay? So what if this guy is moving in this direction, in the y direction, instead of in x direction? Is there any change in terms of the eddy mass? No, because it's exactly symmetric. I mean, it doesn't matter which direction this guy is moving. The eddy mass is exactly the same thing. But on the other hand, if you have a body which like an ellipse, for example, okay, where this is for and whose major axis is, let's say, B, and this guy is A. And then definitely when this guy is moving in this way and this guy is moving that way, they will have a different hydrodynamic force, right? In fact, if you compute in the x direction, eddy mass in the x directional motion is rho. Once again, rho is density of fluid, okay? Pi a square, that's what it is. On the other hand, the same thing in the y direction is rho pi b squared. From homework 2, you know how to compute the flow field around the ellipse. So you can compute the eddy mass, and you will see the eddy mass in the x direction is rho pi a squared, which is exactly the same as the eddy mass for a circular cylinder whose radius is a. Okay. And on the other hand, if this guy is moving in the y direction, the eddy mass is rho times pi b squared, meaning that this eddy mass is exactly the same as a circular cylinder whose radius is b. Okay, so that's what we can find from the solution of Laplace equation when you do exactly the same way. more complicated, the geometry and the motion, you have to, once again solve the Laplace equation and so on. So for a translational motion of an arbitrary body through the body. So you have some complicated geometry like this. So this is body, and if this guy is moving in some direction like this, then how do we get the edit mass? Okay. So the boundary value problem is exactly the same thing, right? And right, at this time we are using moving coordinate system as before. So coordinate system is fixed with fixed on the body, and therefore the normal vector doesn't change. Okay. When normal vector changes when you have a rotational motion. So for translational motion, if you in terms of normal vector, normal vector doesn't change because it has it is fixed with a body, and therefore the only time dependence that you see is here. Okay, so think about it. This guy is moving, or some way, and you have a body coordinate system which is fixed here, and normal vector doesn't change. So the only time dependence that you can see in this problem, so the Laplace equation, you don't see anything. And this one, the only time dependence appears here. Okay, on body surface, but body surface is fixed in a moving coordinate system, and therefore I can write phi. I can pull out the body, the time dependence from the velocity potential in the following way. Okay. So this is strange notation, and now velocity potential has its three components, and I can write this as summation of I1 to this time let's look at 2D. It doesn't matter it's a 2D or 3D. 3D just from 1 to 3, and this time 1 to 2 for 2D. Okay. So U has a component U1 and U2, and phi has a component phi 1 and phi 2. And then d phi dn is nothing but summation I equal to 1 to 2 ui, which depends on time only, and then I have d phi I dn. Okay? And then this guy has to be the same as u dot n, which is summation of I 1 to 2 ui and I. 1 is in the x direction and 2 is in the y direction, as I wrote here. And then, as you can see from here, the boundary condition for phi I is nothing but, this implies d phi di n is ni. Okay? Because I have a ui here, and then I have this guy and this guy. So this time d phi I disqualify, d phi I dn has to be ni. And then you substitute here, you will get exactly the same thing. So at the end, what I have is the following. For I equal to 1 and 2, Laplacian of this guy is equal to 0. Okay. And also, this guy goes to 0. And then d phi I dn is ni on body surface. So I did two things here. First, I dropped time dependence. Okay? Of course, once you solve this problem, then you have to compute real velocity potential in this way. Okay? But when I compute, this phi, I don't have to worry about time dependence. Okay? So that's the one thing that I did. The second thing is, this time I split the translational motion in the x direction and translational in the y direction. So this is, for I equal to 1, you are solving translational motion in the x direction. Circular cylinder in the translational motion in the x direction. Okay? You can think, the velocity is 1. ui and I. So velocity, you can think, velocity is 1. And also when solve I equal to 2, you are solving for the problem in a circular cylinder which is moving in the y direction only. So that's the another thing that I did here. So first I dropped time dependence, and the second I split into x translational motion and y translational motion. Why dropping the time dependence is good? The reason is, once you know geometry, you can solve this problem before you know the motion of the body. Okay, previously, to solve this problem, you have to know what the u is. Okay, this time, I don't have u, time dependence, so I can solve this boundary value problem in advance without knowing what the velocity speed is, body speed is. That's a good thing. Okay. And also, we learned panel method and so on for steady problem. And that panel method can be used here without any modification, because this is time-independent problem. Okay. The only difference is the velocity is 1 this time. But the method that we learned can be applied here without any modification. Okay. So we can use panel method that we developed for steady problem can be applied to this unsteady problem. Also, the reason why we could split in the x and y directional motions is that the problem is linear. Okay. If my governing equation is nonlinear instead of linear, then I cannot do that. Okay. But I could do that because the problem is linear. So far so good? Okay. So all we have to do is solve this by using one of the methods that we learned, multiple expansions, infinite series, source, zinc, dipole, and or other higher multiples. That's one way. Or you use complex variables method that if you know what the component mapping is, or you just use panel method numerically and then compute this. Now, once you solve this boundary value problem, numerically or analytically, and then you can compute force so ith component of the force is nothing but P and I, let's call J. Which way is better? So let me start from phi. So once you solve this problem, and then we have I equal to 1 to 2, ui phi I, right? So time dependence only appears here. And then pressure, hydrodynamic pressure is exactly what we did, correct? And then this guy, time derivative has to be applied only here. And then I have minus rho summation I equal to 1 to 2 ui dot and phi I. And then hydrodynamic force, which is a vector, is given by Pn ds over this, right? That's exactly what we did before. And let's say I'm looking at J's component. It has a 2 component in 2D and 3 component in 3D. So let's say J's component. J can be 1 or 2, right? So I'm looking at J's component. Then I have all I have to do is just multiply pressure by normal vector in the normal component, J's component of normal vector. Okay, that's what I have to do. So far so good? So J's component, I just multiply by pressure by J's component of normal vector. And then we use this expression. And then I have minus rho. And then I can pull out u dot here, because this is only, it depends on time, so it doesn't affect integration. And then I have summation I equal to 1 to 2 phi I and j. Okay, and then I have minus summation. Let me pull out summation. I forgot ds here. I pull out the summation here. I equal to 1 to 2. I forgot I here again. Sorry. So since I have I cannot pull that out yet. So I have to put here. Because I left my summation here. When I pull out the summation, and then I can pull out ui outside of So I have a rho integration of phi I nj ds times ui dot. So what I did is I just pull out this guy outside, and then I just rewrite it. And also I can pull out this guy outside of the integral because this depends on only time. So now you can see this is a force, and this is a acceleration, and therefore this quantity has to have a dimension of mass, which is nothing but eddy mass again. Okay? So let me rewrite it. So Fj is equal to minus summation I from 1 to 2 Mji. As you can see, there are this subscript and this subscript are different. So I call this as Mji, and then ui dot. Yeah. So Mji is equal to rho body surface phi I and j. First subscript represents the direction, the force direction. Okay. The second subscript represents the direction of motion. So in other words, when the body is moving in the ith direction, the body experiences force in the jth direction. If it is circular cylinder moving in the x direction, of course, there is no force in the y direction because it's symmetric. Okay? But if it is not symmetric, then you could have, when this guy is moving in the x direction, you could have force in the y direction. If it is circular cylinder, because you have a top and bottom symmetry, and therefore this guy is moving in this way, the pressure in this side and pressure in this side is exactly the same. So there is no force in this direction. But you only feel force in this direction because body is accelerating or decelerating. Okay. But general body, we are looking at an arbitrary body, which we don't assume any symmetry. And then when this guy is moving in the x direction, you still can have a force in the y direction as well. Of course, you will have a force in the x direction. So you will have a M11, M12, M21, M22. Okay? So there are four, the eddy mass coefficients. So M11, in 2D of course, M12, M21, M22. So this is a force in the x direction due to the motion in the x direction. This is a force in the x direction due to the motion of y direction. This is vice versa, and this is M22. Okay. So once again, when we do this representation, we don't have any time dependence. In other words, we don't have to know how the body moves. All you need to know is body geometry. Once you know body geometry, you can solve this, and then you can compute added mass in advance. This requires only body geometry. This is body geometry. Normal vector is body geometry, is related to body geometry, and phi I depends on only geometry. Okay? So once you know the body geometry, you can compute, pre-compute, this guy. And then once you know the acceleration of the body later, then you can compute force easily by just multiplying by acceleration. Okay? You can do exactly the same thing for the body motion on the free surface, as you can see later. Okay, but there is a little bit more complication there because body is floating and moving on near the free surface or under the free surface, and then the body generates waves, and that will give you another force. But this time in unbounded domain, here we are looking at unbounded problem. Okay, and this is the way to compute hydrodynamic force. Question? I might do the translational motion problem. I'm sorry, rotational motion problem. When I talk about three-dimensional problem. But here, I just use a relatively simple, two translational motion, but almost the same. Okay. So as I said, if the body has some symmetry, then some of these can be zero. For circular cylinder, we know M12, M22, M21 are zero. When body is moving in this direction, you only feel the force in that direction. Also, the ship is moving in the x direction, and ship has a symmetry on the left-hand side and right-hand side. Therefore, there is no force in the transverse direction. Okay, so depending on geometry, some of these can be zero. The other thing that is not so clear but is true is the following. So we can write this as a matrix, right? M11. So this is added mass matrix, and what I'm saying here is this guy and this guy are the same, and so that's a symmetry that so this matrix is symmetric matrix. Okay, and how can I show this is the following. So we use Green's theorem or Green's identity. That it goes like this. Okay, so when you have suppose you have so you have a volume of fluid, and if this guy is zero, because where psi and phi are the solutions of the Laplace equation. Then this guy is 0, this guy is equal to 0, right? And then the left-hand side, I can write this way. So this integral is 0 because psi and phi are the solutions of the Laplace equation. And then I can, if I just use a vector identity, I can write this way. The reason is, first one gives, grad phi dot grad psi and grad psi dot grad phi. So I have minus sign, so they cancel each other. And then I end up with this, okay? So I can rewrite this guy in this way. And then we can use, Gauss theorem, and which is so I change volume integral to surface integral, and then I end up with phi ds. Okay? Which is nothing but, by definition, n dot grad psi, which is and n dot grad phi is d phi dn, is equal to 0. So this implies has to be equal to okay? So far, I haven't used anything other than, psi and phi are the solution of Laplace equation. And then I can show this is equal to this, okay? Now, in our problem, we have a arbitrary body here. And also we have a boundary at infinity, and this is V, okay? At infinity, I said grad phi goes to 0, right? So then I don't have to worry about this. So then I can change, this guy to S, which is S. So S is SB plus S infinity. But S infinity, the contribution is 0 because of that. Okay? And therefore, I can just replace, S by S sub B, the body integration over body surface. Now, Mij or MJI, MJI is equal to rho phi I nj ds S of B, right? Because of that boundary condition, I can rewrite nj by d phi j dn ds on body surface. So I use the following body boundary condition. D phi j dn is nj on body surface. So I can replace this to d phi j dn. Okay? And this phi I and phi j both satisfy Laplace equation. Therefore, I can use this. So this means, so this time, my phi is phi I, and this psi is phi j. Then, from this, the Green theorem, Green's identity, I can write this as phi j d phi I dn ds. This is from Green's identity. So I switch j and I. I have phi I, phi j, and then I can switch. And this is exactly m I j by definition. Or I can go one more step. Is equal to rho phi j ni ds. Because once again, body boundary condition said this is ni from body boundary condition. And that is nothing but mij. So I showed that mji is equal to mij. So added mass coefficient, a matrix that I wrote here, is symmetric. Is an asymmetric matrix. Okay? So that's what I showed here. The reason why I could do that is this phi I, phi j both satisfy Laplace equation, and we use this property, this identity on the body surface or that boundary condition. Okay. Any question? So M12 is 0, then M21 has to be 0. Okay, because of that. Which is the case for a circular cylinder, for example, and also for the ellipse. Because it has a symmetry, top and bottom symmetry. Also, it has a before and after symmetry for the circular the ellipse. So that gives you this off diagonal terms, 0 off diagonal terms. Okay, so the midterm exam, which you will take on this coming Tuesday, include material up to this point. Okay. So some instruction for homework, for exam. Midterm exam. I want to start the exam a little early than our regular class time. So 30 minutes, earlier. No, 10:20. Okay. So slightly less than 2-hour exam. This is what you can bring. You can bring any but a single textbook of your choice. And then you can bring a course note, your course notes, plus homework. Of course, I didn't give them many, but any handouts. Yeah. So, so far, we discussed the following, following topics. So we talked about first at the beginning of the, class, we talked about conservation of mass, right? And then we end up with so the total mass has to be conserved. Volume can change depending on the compressibility, but total mass has to be conserved, and that will give you d rho dt plus rho by using the transport theorem. And this guy, we assume this guy is a 0 because of incompressibility. And then we end up with this guy equal to 0. Okay, so water is incompressible, and therefore we assume, we impose, divergence-free velocity condition. And then we use, conservation of momentum, linear momentum, and which says d dt rho u dv. So m is a material derivative, volume. So you are looking at always, the same fluid volume. And this guy, so if you see any change of linear momentum, that has to come from, the external force applied. So when the force is applied, the momentum of fluid changes. So that force can be, surface force, or it can be body force, like a gravity. Okay? And surface force is, the pressure, just contact, and also it can be, has a, friction, and also, so the one is, the pressure, the other is viscous stress, and that's what you end up with. And so the Galvani equation that we have is this and that, and that's the Galvani equations, right? Because we assume rho is constant. So for this class, we assume rho is constant. And then you solve Navier-Stokes equation. Okay, so we have 4 unknowns for 4 equations for 4 unknowns, 3 velocity components and the pressure. And typically we have to impose boundary conditions, and whenever we have boundaries, and when the rigid boundary, the boundary condition for velocity is an oscillator boundary condition. Okay. And then we talked about vorticity, which is defined curl of velocity vector. And so the equation of vorticity so when you take a curl of this guy, you get this. And here, this is a material derivative, right? So we often write du dt. So this is really acceleration of fluid particle when you follow fluid particle, just like this. And this guy is material derivative of omega. For 2D, I have only one component. So I have d omega dt. So this is a component in the z direction, has to be equal to, this term disappears for 2D, and that's what we have. If the fluid is inviscid, then this term disappears and vorticity is conserved. Okay, if this guy is 0. So if the right-hand side is equal to 0 over here, then there is no forcing, and therefore the fluid will have 0 vorticity if you neglect viscosity at the boundary. If you have a viscosity at the boundary, if you have viscosity, then the boundary can generate the vorticity, even though the vorticity is 0 at t equal to 0. But if you neglect viscosity, then you allow slip, and therefore vorticity cannot be generated on the boundary. Therefore, if the flow is irrotational at t equal to 0, then vorticity has to be 0 all the time. And also, I discussed, I introduced, stream function psi or psi in this way. So that for two-dimensional problem, we can introduce, stream function psi, and that's how we define, the right, vorticity in terms of stream function. And then we talked about rotational motion by assuming vorticity is 0 all the time, because we start from 0 vorticity with nu equal to 0. Okay, the viscosity is identically 0. Since this guy is 0, U can be written in terms of a gradient of a scalar function, which we call velocity potential. Okay, and once you have that, then because of this, we end up with a Laplace equation, single equation for a single unknown. And then this Euler equation will give you Bernoulli, equation. So you have to know what the Bernoulli equation is, how you get that. Okay. So the next step you learned is how to solve Laplace equation then. Okay. So once you know Laplace equation, you can find the pressure from Bernoulli equation. So you have to find the velocity potential, and so I introduce general solution by using using separation, the separation of variables. So we assume function depends on only x and z. The product of two functions, one depends on x only, and the other depends on only z, and then you can find the solution. And so at least you should know what the source is or sink is, and also you have to know how to what is dipole and vortex. I think those are the three things that I discussed in the class in detail. So you have to know these three, how to write the potentials for source, dipole, and vortex. Okay. And also at least you have to know the velocity potential solution for a circular cylinder. I haven't made exam yet, but I'll ask something related to circular cylinder for sure. Yeah. So just go through the steps to get the solution for a circular cylinder. Okay. And then I talked about today and on Tuesday added mass for unsteady translational motion. Okay, these are the topics for the midterm exam, and not much, huh? So I reviewed in 15 minutes. So but anyway, unfortunately, I won't be here in the exam because I have travel to the United States, next week, and therefore I will cancel, Thursday class, and then I will, give you a makeup lecture after I come back. Okay. So I wish you good luck, and see you in 2 weeks.